The human body is a miracle of evolution, perfectly tuned for life on a single pale blue dot. But what happens when you take it somewhere it was never meant to exist? Tonight, we're journeying through 100 extreme ways the cosmos would transform, challenge, and ultimately overwhelm the fragile vessel you call home. From the first breathless second to effects so strange they seem like science fiction. Welcome to Midnight Science. This channel is dedicated to the art of falling asleep while falling deeper into wonder. Each of these revelations explores the beautiful brutality of a universe indifferent to our survival at a pace designed for late-night contemplation and peaceful drift. Hopefully, this won't be too unsettling to keep you awake. But if it is, at least you'll drift off somewhere along this journey through what space does to flesh and bone, each effect a little stranger than the last, learning as you let go. Because once you understand how fragile we really are, every breath on this planet becomes a quiet miracle. The first of these transformations begins the instant you leave Earth behind. There is a moment just after launch when the body realizes it has been betrayed, not by the spacecraft, not by the mission, but by the universe itself. For billions of years, life on Earth has been shaped by a single, relentless force: gravity. Every cell, every fluid, every bone has been sculpted by it. The body knows which way is down. It knows how to stand, how to pump blood upward against the pull, how to sense the horizon without thinking. And then, in an instant, all of that ends. Space does not announce itself with violence. There is no sudden pain, no alarm that screams through the body. Instead, it begins quietly, intimately, a whisper in the blood, a shift in the skull. The body, for the first time in its existence, must navigate a world that has no up or down, no weight, no anchor. This is where the unmaking begins. Inside the spacecraft, radiation moves like a ghost. It passes through metal walls as if they were fog. It slips past the thin barriers of skin and bone, entering the soft tissue of the brain without resistance. These are not the familiar rays of sunlight that warm the Earth. These are cosmic particles, fragments of exploded stars, solar winds, galactic collisions, traveling at nearly the speed of light. When they strike a neuron, they leave behind something invisible but devastating: inflammation. The brain, in its ancient wisdom, tries to respond. Immune cells awaken. Chemical signals flood the tissue. But this is not an infection that can be fought. This is damage at the level of physics itself. The neurons begin to misfire, synapses slow. The delicate networks that govern thought, memory, reaction time, all of it starts to fray. Astronauts have described it in hushed tones, a fogginess, a sense that thoughts take longer to arrive, that decisions, once automatic, now require conscious effort. They call it a space brain, though the term feels too casual for what it represents. Because this is not just fatigue. This is the brain being quietly rewritten by the cosmos. How long does it take before the damage becomes permanent? No one knows for certain. The longest missions have been measured in months, not years. But the data we do have is troubling. Neuroimaging studies show changes in brain structure even after short stays aboard the International Space Station. White matter integrity decreases. Gray matter volume shifts. The hippocampus, the seat of memory, shows signs of atrophy. And these are astronauts who were only in low Earth orbit, still partially shielded by the planet's magnetic field. Beyond that protective bubble, in deep space, the radiation intensifies. On a journey to Mars, the exposure would be far worse. By the time a crew arrived, their brains would have absorbed doses equivalent to hundreds of chest X-rays. Not all at once, not dramatically, just a constant, invisible erosion. The question is not whether the brain will change. The question is whether it will still be recognizably human when it does. But radiation is only one half of the assault. The other comes from within. On Earth, gravity pulls blood and fluid downward, pooling it in the legs and lower body. The heart works against this pull, pumping steadily upward. The body has calibrated itself to this struggle over millennia. It is written into the architecture of every vein, every valve, every pressure sensor. In microgravity, that calibration fails. Without the downward pull, fluid drifts upward. It pools in the chest. It rises into the neck. It floods into the skull. Astronauts often describe their faces feeling puffy, swollen, as if they are perpetually hanging upside down. Their sinuses clog, their voices change. They look to ground control cameras like distorted versions of themselves. But the real damage is happening where no camera can see. Inside the skull, pressure begins to build. The brain floats in cerebrospinal fluid, a delicate suspension system that cushions it against shock. On Earth, this fluid drains naturally, flowing down through the spinal column. In space, it has nowhere to go. It accumulates, the pressure rises, and the brain, locked inside the rigid cage of the skull, begins to be compressed from within. The eyes are the first to suffer. The optic nerve, which connects the retina to the brain, begins to swell. The shape of the eyeball itself distorts, flattening slightly at the back. Vision blurs. Some astronauts report seeing halos around lights. Others find they can no longer focus on close objects, their near vision deteriorating in a matter of weeks. This condition has a name: spaceflight-associated neuroocular syndrome, SANS for short. It sounds clinical, manageable, but what it represents is something far more unsettling. It is the body being reshaped by an environment it was never designed for, and the changes do not always reverse. Some astronauts return to Earth with permanent vision loss. Their eyes, once pressed outward by the fluid, never fully regain their original form. The optic nerve, once swollen, remains subtly damaged. They adapt. They use reading glasses. They cope. But the question lingers. What happens on a mission to Mars, where there is no quick return, where the pressure builds not over weeks but over months or years? At what point does adaptation become irreversible decline? And then there are the muscles. On Earth, muscles exist in constant tension. Even when sitting still, they are working, holding the spine upright, balancing the head, resisting the endless pull of gravity. This is not effort. This is baseline. The body does not know any other way. In space, that tension vanishes. Muscles no longer need to hold anything up. The body drifts, weightless. At first, it feels like freedom. Astronauts float through corridors, spinning effortlessly, delighting in the sensation. But the body interprets this freedom as obsolescence. If the muscles are not needed, why maintain them? Within days, atrophy begins. It starts with the legs, the calves, the thighs, the glutes. These powerful engines of movement on Earth begin to waste away. The fibers shrink. The mitochondria, the tiny power plants inside each cell, start to shut down. Strength drains away at a startling rate. Studies estimate that astronauts lose up to 20% of their muscle mass on missions lasting just 5 to 6 months. But the loss is not uniform. Fast twitch fibers, the ones responsible for quick, explosive movements, deteriorate faster than slow twitch fibers. The body is not just getting weaker, it is losing the ability to react. The early Soviet cosmonauts knew this terror firsthand. Yuri Gagarin, the first human in space, spent only 108 minutes in orbit. When he returned, he could walk. But later missions, longer missions, told a different story. Cosmonauts who had spent weeks aboard space stations returned to Earth unable to stand. Their legs buckled, their balance failed. Some had to be carried from their capsules, their bodies too weak to support themselves in Earth's gravity. The Americans saw the same. After Skylab missions in the 1970s, astronauts stumbled on the aircraft carrier deck, their muscles hollowed out, their bones brittle. They looked like they had aged years in a matter of months, and this was before anyone had spent even a full year in space. The body, it seems, remembers gravity even when gravity is gone. But it does not wait patiently for its return. It adapts. It reconfigures. It begins to shed the weight of evolution, piece by piece. Muscles dissolve. Bones demineralize. The cardiovascular system, no longer needing to pump blood upward, grows lazy. The heart itself shrinks, becoming smaller, weaker, more efficient for a weightless world, but catastrophically unprepared for the one it left behind. And all of this happens quietly, without pain, without warning. The body does not resist space, it surrenders to it. These changes are only the body's first whispers, the quick, surface-level unraveling. But deeper inside, time itself begins to move strangely. There is a clock inside every cell of your body. It does not tick, it does not chime, but it counts relentlessly the passage of time. With each division, each replication, each moment of stress, the clock winds down. The body ages, the machinery wears, and eventually, inevitably, it stops. This is how we understand aging, as a countdown, a slow march toward an end that cannot be reversed. But in space, something impossible happens. The clock runs backward. It was discovered almost by accident. In 2016, NASA astronaut Scott Kelly returned to Earth after 340 days aboard the International Space Station. His body was exhausted, his muscles had withered, his bones had thinned. He looked, by every visible measure, like a man who had aged far beyond a single year. But when scientists examined his cells, they found something extraordinary. His telomeres had grown longer. Telomeres are the protective caps at the ends of chromosomes, like the plastic tips on shoelaces that keep them from fraying. Every time a cell divides, these caps shorten. It is the biological clock of aging made visible. Shorter telomeres mean older cells, closer to the end of their functional life. Longer telomeres mean youth, vitality, the potential for renewal. And Scott Kelly's telomeres, against all logic, had lengthened in space. For a brief moment, it seemed like a miracle. Had space somehow reversed aging? Had microgravity triggered some hidden mechanism of rejuvenation, dormant on Earth, but awakened beyond its pull? The implications were staggering. If telomeres could be extended in orbit, could space travel become not a journey into decay, but into preservation? But the euphoria did not last. Within months of returning to Earth, Scott Kelly's telomeres collapsed. They did not simply return to their pre-flight length. They shrank even shorter than before. The cells, it seemed, had not been rejuvenated. They had been stressed, pushed to their limits. And when they returned to gravity, they broke. The telomere paradox, as it came to be known, is still not fully understood. Some researchers believe the lengthening was a survival response, a desperate attempt by the body to repair damage from radiation and oxidative stress. Others think it may be linked to inflammation, a biological alarm system going haywire in an environment it cannot comprehend. But the collapse afterward suggests something darker, that the body, in space, is not adapting, it is fighting. And when the fight ends, it loses. What does it mean for a cell to age faster than the body that contains it? On Earth, aging happens gradually. Decades pass before the signs become visible. Gray hair, wrinkled skin, slower reflexes. The process is so slow that we barely notice it day to day. But at the cellular level, the countdown is constant. Telomeres shorten. DNA accumulates errors. The machinery that repairs damage begins to falter. In space, this process accelerates. Studies of astronauts show that even short-term missions trigger molecular changes equivalent to years of aging on Earth. The immune system weakens, inflammatory markers spike, cellular repair pathways, honed over millions of years of evolution, begin to misfire. The body is not just older, it is confused, and the telomeres are only one part of the puzzle. Deep inside every cell, there are structures so small they can only be seen through the most powerful microscopes. Mitochondria, the powerhouses of the cell, the engines that convert oxygen and nutrients into the energy that fuels every heartbeat, every thought, every breath. They are ancient, descendants of bacteria that merged with our ancestors billions of years ago. They have their own DNA, separate from the nucleus, their own evolutionary history. And in space, they begin to fail. Microgravity distorts the way mitochondria function. Without the constant pull of gravity, the internal structures that regulate metabolism lose their orientation. The flow of ions across membranes becomes erratic. Energy production drops. Waste products accumulate. The result is a kind of cellular exhaustion. Astronauts report feeling tired in ways that sleep does not fix. Their muscles fatigue more quickly. Their cardiovascular systems struggle to keep up. At the molecular level, their cells are starving for energy even as they float in an environment that demands less of them. It is a paradox. The body is working harder to do less. But the damage goes deeper still. Mitochondria do more than just produce energy. They are sensors. They detect stress. They trigger programmed cell death when damage becomes irreparable. They regulate inflammation. They communicate with the nucleus, switching genes on or off in response to the environment. In space, this communication breaks down. Studies of mice flown on the International Space Station show that mitochondrial DNA becomes riddled with mutations. The proteins that protect against oxidative stress degrade. The cells enter a state called senescence, a kind of living death, where they no longer divide but refuse to die. These senescent cells accumulate, releasing toxic chemicals that damage their neighbors. On Earth, the body has mechanisms to clear them out. In space, those mechanisms falter. The question is not whether deep space will accelerate cellular aging. The question is, how much, and whether it can be stopped. Because the telomeres and mitochondria are not the only things changing. The genome itself is being rewritten, not in the way that creates new species or alters inherited traits, but in the patterns of which genes are active and which are silent. This is epigenetics, the layer of molecular switches that sits atop the DNA, turning genes on or off in response to the environment. And in space, hundreds of these switches flip. Scott Kelly's mission revealed something astonishing. After nearly a year in orbit, more than 7% of his gene expression had changed. Genes involved in immune function, DNA repair, bone formation, and oxygen regulation were behaving differently than they had on Earth. Some had ramped up their activity. Others had gone quiet. It was as if his body had been reprogrammed. Many of these changes reversed when he returned to Earth, but not all of them. Years after his mission, some genes remained altered. The body had not fully reset. It had been marked by space, change at a fundamental level that persists even now, long after gravity reasserted itself. What does this mean for a journey to Mars? For a mission that lasts not 1 year, but 3 or 4? For a generation born and raised beyond Earth's pull? If the genome is rewritten in space, if the molecular machinery that defines what it means to be human is altered, then the question becomes unavoidable. Is the spacefaring human still the same species on a molecular level? There is a concept in biology called plasticity. It is the ability of an organism to adapt to new environments, to reshape itself in response to changing conditions. Life on Earth is full of examples. Fish that change sex depending on their social environment. Plants that grow taller in shade, broader in sunlight. The human body itself is astonishingly plastic. Muscles that grow or shrink, bones that strengthen or weaken, immune systems that learn and forget. But plasticity has limits. There is a point beyond which adaptation becomes transformation, where the changes are so profound that the organism can no longer return to what it was. This is the edge that space pushes toward. The body does not simply weaken in microgravity, it reconfigures. It becomes something optimized for a weightless environment. The heart grows smaller because it does not need to pump against gravity. The bones shed calcium because they do not need to support weight. The immune system, exposed to constant low-level stress, recalibrates its baseline. These are not temporary adjustments. These are evolutionary pressures compressed into the span of a single lifetime. And the genome responds. Scientists call it differential gene expression. It sounds technical, sterile, but what it describes is extraordinary. The same DNA can produce entirely different outcomes depending on which genes are active. A caterpillar and a butterfly have identical genomes, yet they are unrecognizable as the same creature. The difference is not in the code, it is in the reading of the code. In space, the human body begins to read its genome differently. Genes that were silent on Earth awaken. Others go dormant. Pathways that govern inflammation, stress response, cellular repair, all of them shift. The body is not mutating. It is translating itself into a new language. And the most unsettling part is this. We do not yet know if that translation is reversible. Imagine a crew on a Mars mission, 3 years, maybe 4, living in microgravity during the journey, then adapting to Mars's gravity. 38% of Earth's, just enough to feel the pull, but not enough to restore what was lost. By the time they return, their genomes will have been in flux for years. Will their telomeres lengthen and collapse again and again, each cycle leaving them shorter than before? Will their mitochondria, stressed beyond recovery, fill their cells with senescent husks? Will their immune systems, rewritten by months of cosmic radiation and isolation, still recognize the pathogens of Earth? Or will they return fundamentally changed, their bodies no longer quite at home in the world that made them? There is a darker possibility that the changes are cumulative, that each mission adds another layer of alteration, another shift in gene expression, another shortening of telomeres. That the body, like a piece of paper folded and unfolded too many times, eventually tears. And if that is true, then the dream of becoming a spacefaring species may come with a hidden cost. Not just the risk of immediate danger, radiation, vacuum, mechanical failure, but the slow, invisible erosion of what it means to be human. The clock inside our cells is not just counting down, it is being reset over and over in ways we do not fully understand. If individual cells transform in space, what happens when they are asked to create new life? There is a dream we carry with us when we imagine leaving Earth. Not just the dream of exploration, not just the romance of distant worlds and alien sunrises, but something deeper, more primal. The dream that wherever we go, we will continue. That life, once kindled on this small blue world, can be carried forward into the cosmos. That children will be born under different skies. That humanity will not merely visit space, but inhabit it. Generations rising and falling among the stars. It is a beautiful dream, and it may be impossible, because there is something we have never done in all our decades of spaceflight, something so fundamental to the continuation of any species that its absence should terrify us. We have never successfully conceived, gestated, and birthed a mammal in space. Not once. Not ever. The experiments that have been conducted tell a story we do not want to hear. In the 1990s, pregnant rats were sent to orbit aboard the space shuttle. They gave birth in microgravity. The pups arrived alive. But something was wrong. Their inner ears, the delicate organs that govern balance and spatial orientation, had not developed properly. On Earth, these structures form in response to gravity's constant pull. In space, without that signal, they grew malformed. The pups could not tell which way was up. They tumbled, they spun, and when they were brought back to Earth, they could not adapt. Their brains had been wired for a world that did not exist. Other experiments followed. Fish embryos that developed with curved spines. Frog eggs that divided chaotically. Their cells migrating in patterns that made no biological sense. Salamander embryos that grew extra limbs, or none at all. Each experiment revealed the same haunting truth. Gravity is not just a force that holds us to the ground. It is an architect, a guide, a constant whisper that shapes every cell, every tissue, every organ as life unfolds from a single fertilized egg. And in space, that whisper is silent. Without it, development does not simply proceed differently, it proceeds wrongly. The body does not know where to place bone. It does not know how to orient muscle. The signals that tell a cell to become heart or lung or limb arrive garbled, confused, lost in the noise of an environment that evolution never imagined. What happens to a human embryo in that silence? We do not know, because no one has been willing to find out. There are ethical boundaries so profound that even in the pursuit of knowledge, they remain uncrossed. No human embryo has ever been conceived in space. No pregnancy has ever been attempted beyond Earth's atmosphere. The risk is too great, the unknowns too vast. But the question does not go away simply because we refuse to ask it. If humanity is to become a spacefaring species, if we are to establish colonies on the moon or Mars or beyond, then at some point, a child will have to be born there, conceived in microgravity or partial gravity, carried through 9 months of development in an environment for which the human body has no template. And we have no idea if that child will survive. The first challenge is the skeleton. On Earth, bones form in response to mechanical stress. The fetus, floating in amniotic fluid, still experiences the pull of gravity. The mother's body presses against it. Movement creates tension. And the cells that will become bone respond to these forces, laying down calcium in precise patterns, building the architecture that will one day support a walking, running, upright human being. In microgravity, those forces vanish. The fetus drifts, weightless, inside the womb. There is no pressure, no resistance. The cells that would normally become bone receive no signal to harden. Studies of developing animals in space show that skeletal formation is delayed, incomplete, or distorted. The bones that do form are thinner, weaker, less dense. If a human child were born in space, would their bones be strong enough to support them when they finally encountered gravity? Or would they collapse under their own weight the moment they tried to stand? The second challenge is muscle. Muscles, like bones, develop in response to use. Even in the womb, a fetus moves constantly, kicking, stretching, pressing against the walls of the uterus. These movements are not random. They are the body teaching itself how to move, how to coordinate, how to exist in a world governed by physical forces. In space, those movements lose their meaning. Without gravity to resist, the fetus's kicks do not build strength. The muscles do not learn to bear weight because there is no weight to bear. Animal studies suggest that muscle fibers develop abnormally in microgravity, lacking the structure and organization needed for coordinated movement. A child born in space might have muscles, but would they have the strength to crawl, to lift their own head, to take even a single step if they were ever brought to Earth? And then there is the heart. The fetal heart is one of the first organs to form. It begins beating just weeks after conception, a tiny flutter that will continue for the rest of a human life. On Earth, the heart develops with a specific task in mind, to pump blood upward against gravity, ensuring that every part of the body receives oxygen. But in microgravity, there is no upward. The heart still beats, blood still flows, but the cardiovascular system has no reason to develop the strength needed to fight against a constant downward pull. Studies of astronauts show that the heart becomes smaller and weaker in space, adapting to an environment where pumping blood requires less effort. What happens to a heart that forms in that environment from the very beginning? Does it develop at all in the way a human heart is meant to? Or does it become something optimized for weightlessness, fragile, and inadequate for any world with gravity? These are questions about architecture, about structure, about the physical scaffolding of a human body. But there is something even more fundamental at stake, something written in the code itself. Every human being begins as a single cell, a fertilized egg containing the complete blueprint for an entire person. Within hours, that cell divides, then divides again, and again. Each division must be perfect. Each strand of DNA must be copied without error. Each chromosome must separate cleanly, precisely, into two identical sets. On Earth, this process is already delicate. Errors occur, mutations arise. Most embryos with significant chromosomal abnormalities never develop past the first few weeks. In space, the risk multiplies. Cosmic radiation, those ghostly particles that slip through spacecraft walls and astronaut bodies without resistance, do not spare the most vulnerable cells. They strike the DNA of a dividing embryo just as readily as they strike the brain of an adult. But the consequences are far worse. An adult cell, damaged by radiation, might malfunction, might become cancerous, might die. But the body, with trillions of cells, can't afford the loss. An embryo cannot. At the earliest stages of development, there are only a handful of cells. If one of them is damaged, if its DNA is broken or rearranged by a cosmic ray, the error is copied into every cell that descends from it. The mutation becomes part of the foundation, and the embryo, if it survives at all, carries that flaw forward into every tissue, every organ, every part of its body. Studies of radiation exposure during pregnancy on Earth show that even small doses increase the risk of birth defects, developmental delays, and childhood cancers. The radiation levels in space are orders of magnitude higher. On the International Space Station, astronauts are exposed to doses equivalent to several chest X-rays per day. For a developing embryo, that exposure would be catastrophic. Some mutations would be lethal, causing the pregnancy to fail before it ever became visible. Others would be subtler, a heart valve that does not close properly, a neural tube that does not seal, an immune system that never learns to distinguish self from invader. And some mutations, the ones that strike at the right moment in the right cells, would create something we have no name for. A human body shaped by forces no human has ever encountered before. Is that still human, or is it something else? The question is not hypothetical. If we are serious about establishing a permanent presence beyond Earth, if we imagine cities on Mars or habitats in orbit, then children will be conceived there. It is inevitable. Human beings do not stop being human simply because they leave their planet. The drive to reproduce is as fundamental as the drive to breathe, but the environment will not care about our intentions. Radiation will not pause for a pregnancy. Microgravity will not adjust itself to accommodate a developing fetus. The cosmic environment is indifferent. It does not protect the vulnerable. It does not make exceptions. And so, the question stands, unanswered and urgent. Can humanity reproduce away from Earth at all? Or are we a species forever bound to this single planet for every birth that will ever be? There are those who argue that we will find a way, that artificial gravity can be created through rotation, that shielding can be improved, that prenatal monitoring and genetic screening will catch problems before they become irreversible. That medical technology will advance to the point where even a child born in space can be supported, augmented, repaired. Perhaps they are right, but we are not there yet. And the dream of interplanetary civilization depends on solving a problem we have barely begun to study. Not the problem of rockets or propulsion or life support systems. Not even the problem of keeping adults alive in space for months or years. The problem of creating new life, of taking 2 cells and allowing them to become a trillion, of guiding that transformation through 9 months of exquisite vulnerability in an environment that offers no evolutionary precedent, no biological roadmap, no guarantee of success. Every species that has ever existed has reproduced in the environment where it evolved. Birds in air, fish in water, mammals on land. The conditions under which life begins are inseparable from the conditions under which it continues. Humanity evolved under one precise set of conditions. One gravitational constant, one atmospheric pressure, one level of background radiation filtered through a protective magnetosphere and atmosphere. Strip those conditions away, and we do not know what we become. Perhaps we adapt. Perhaps the body, in its astonishing plasticity, finds a way to build itself even in the void. Perhaps the children of Mars will be different, yes, but viable, capable, human enough, or perhaps there is a threshold, a line beyond which human development cannot proceed, a boundary written not in law or ethics, but in biology itself. We will not know until we try, and trying means risking the life of a child who never asked to be an experiment. This is the unspoken weight carried by every vision of humanity's future in space. Not just the danger to those who choose to go, but the danger to those who have no choice. The unborn, adrift in the void, their bodies shaped by forces we cannot fully control or predict. If we cannot bring children safely into the world beyond Earth, then every habitat, every colony, every settlement becomes a dead end. A place where humans can visit, but never truly live, never continue, never become more than transient guests in a cosmos that will outlast us all. Even the adults who leave Earth must negotiate with forces older than life itself, forces that gnaw at bone, marrow, and memory. There is a kind of violence that does not announce itself. No sudden blow, no visible wound. Just a slow, persistent unmaking that happens in the dark, beneath the skin, where no one can see. In space, this violence is constant. It begins the moment gravity releases its hold. The body, freed from the weight it has carried for millions of years, does not celebrate. It does not adapt gracefully to this new lightness. Instead, it begins to dissolve itself. Bone is not static. This is something most people never consider. We think of our skeletons as fixed structures, solid frameworks built once in childhood and maintained forever. But bone is alive. It is constantly being broken down and rebuilt, torn apart and reconstructed, in a delicate balance that has been perfected over evolutionary time. On Earth, this balance is maintained by forces we take for granted. Every step, every movement, every moment of standing upright creates tiny stresses in the bone, and the body responds to these stresses by reinforcing the skeleton, laying down new calcium, strengthening the structure that bears our weight. Remove the weight, and the body stops reinforcing. In microgravity, astronauts lose bone at a rate that should not be possible, 1 to 2% of bone mass per month. It sounds abstract, a small number, but consider what it means. On Earth, osteoporosis, the disease that causes bones to become brittle and fragile, develops over years, even decades. The elderly lose bones slowly, gradually. As age diminishes the body's ability to rebuild what time breaks down. In space, that same process happens 12 times faster. An astronaut on a 6-month mission can lose as much bone density as a postmenopausal woman loses in a decade. The skeleton does not thin evenly. It concentrates in the places that bear the most weight on Earth: the hips, the spine, the legs. The very structures that allow us to walk, to stand, to move through the world with confidence. And the loss does not stop when the mission ends. This is the part that haunts researchers. When astronauts return to Earth, their bodies begin to recover. Exercise programs are prescribed, calcium supplements are given. The skeleton, sensing the return of gravity, starts to rebuild. But it never comes all the way back. Studies tracking astronauts for years after their missions show that bone density improves, yes, but it plateaus. It reaches a new baseline, lower than before. Some of what was lost is gone permanently. The skeleton remembers its time in space. It carries the memory in its structure, in the gaps where calcium should be but will never return. After one mission, this might be manageable. The loss is significant but not catastrophic. But what about a second mission? A third? What about a journey to Mars that lasts not 6 months, but 3 years? The body is governed by two types of cells that work in opposition: osteoblasts, which build bone, and osteoclasts, which break it down. On Earth, these cells exist in balance. The stress of movement signals the osteoblasts to build. The absence of stress allows the osteoclasts to clear away old, damaged bone so it can be replaced with new. It is a cycle of destruction and renewal that keeps the skeleton strong, responsive, alive. In microgravity, the balance collapses. The osteoblasts, sensing no stress, no weight, no reason to build, go quiet. They slow their activity. They stop laying down new bone. Meanwhile, the osteoclasts continue their work, breaking down and clearing away bone as if nothing has changed. It is not that the body is confused. It is doing exactly what evolution has taught it to do. If bone is not being used, why maintain it? The body is optimizing itself for an environment where weight does not exist, where the skeleton is no longer a weight-bearing structure, but a vestigial framework, unnecessary and expensive to maintain. And so, it discards it. The calcium that once formed the skeleton does not simply disappear. It floods into the bloodstream, creating new problems. Elevated calcium levels can lead to kidney stones, a painful and dangerous condition made worse by the fact that astronauts are already dehydrated, their bodies struggling to regulate fluid in microgravity. Some astronauts have reported passing kidney stones during missions. The pain is excruciating, incapacitating, and there is no emergency room in space, no surgical intervention, just time and hope, and the knowledge that the body is cannibalizing itself. The calcium also deposits in soft tissues, in blood vessels, in places it was never meant to be. Over time, this can contribute to cardiovascular problems, arterial stiffness, conditions that compound the other ways space damages the heart. The skeleton is not just weakening, it is poisoning the rest of the body as it breaks down. Engineers have tried to solve this problem. Astronauts on the International Space Station exercise for hours every day. Treadmills with resistance harnesses simulate the impact of running. Resistance machines mimic weightlifting. The goal is to trick the body into thinking it is still on Earth, still bearing weight, still needing its bones. And it helps. The bone loss is slower with exercise, but it does not stop. Even with the most rigorous exercise regimens, astronauts still lose bone. The artificial stress is not the same as real gravity. The body knows the difference, and it continues to dissolve the skeleton month by month, relentlessly. What happens on a mission to Mars? The journey alone takes 6 to 9 months, depending on the alignment of the planets. Then there is the time on the surface, at least a year, possibly longer, waiting for the next launch window to open. Then another 6 to 9 months for the return journey, 3 years minimum. During the journey, the crew would be in microgravity, losing bone at the accelerated rate. On Mars, they would experience gravity again, but only 38% of Earth's. Enough to feel weight, but not enough to fully signal the body to rebuild. By the time the crew returned to Earth, their skeletons would be devastated. Scientists have run the numbers. The estimates are grim. After 3 years, bone density in the hips and spine could be reduced by 30% or more. At that level, the risk of fracture becomes catastrophic, not just from falls or impacts, but from ordinary movement, from standing, from walking. The bones could break under the weight of the body they were meant to support, and this assumes the crew survives the landing. The return to Earth gravity after years in space would be a shock to every system. The heart, weakened and small, struggling to pump blood. The muscles, atrophied and frail, barely able to lift limbs that suddenly weigh again. And the skeleton, hollow and fragile, bearing a load it can no longer sustain. There is a point of no return, a threshold beyond which the damage cannot be undone, where the body has shed so much of its structural integrity that no amount of rehabilitation can restore it. We do not know exactly where that threshold is. It has never been tested, No human has stayed in space long enough to cross it, but it exists, and a Mars mission would bring us dangerously close. Some have proposed solutions: artificial gravity generated by rotating spacecraft, pharmacological interventions to stimulate bone growth, advanced materials that could support the skeleton externally, mechanical exoskeletons that bear the weight the bones no longer can. These are not fantasies, they are possibilities, but they are also admissions. Admissions that the human body, as it is, cannot survive the journey, that we would need to be augmented, supported, fundamentally altered to endure what space demands of us. There is something deeply unsettling about this realization. For all of human history, our bodies have been enough. We have crossed deserts and oceans, climbed mountains, and descended into caves. We have adapted to extremes of heat and cold, altitude and depth. The body, in its remarkable resilience, has carried us to every corner of the earth. But space is different. Space does not care about resilience. It does not reward adaptation. It simply removes the conditions under which the human body was designed to function, and waits to see what remains. And what remains, after months or years in microgravity, is something diminished, not broken necessarily, not destroyed, but eroded, hollowed out, a structure that once bore weight and moved with confidence, now fragile and uncertain. The skeleton, the literal foundation of the human form, becomes porous, brittle, a lattice of calcium that can no longer trust itself. This is not science fiction, this is not speculation, this is what happens, measurably and inevitably, to every human who spends significant time beyond Earth's pull. The question is not whether bone loss occurs. The question is whether it can be stopped. And if it cannot, how much loss is survivable? How weak can the skeleton become before the astronaut is no longer an explorer, but a patient? Before the mission becomes not a journey of discovery, but a medical emergency waiting to happen. We celebrate the courage of astronauts, their willingness to leave Earth, to venture into the unknown, to risk their lives for the sake of knowledge and exploration. But we do not always acknowledge the price they pay, not just the risk of accident or catastrophic failure, but the certainty of damage, the slow, invisible erosion that begins the moment they enter orbit and continues, day after day, until they return. They come back changed, weaker, their bodies marked by an environment that does not forgive, does not forget. And they know when they go up that this will happen. They accept it. But acceptance does not make it less real. The bone density scans tell the story. The height measurements show the truth. Astronauts return taller, their spines stretched by the absence of compression, only to shrink again when gravity reasserts itself. The X-rays reveal the thinning, the gaps, the places where the skeleton has given up mass in exchange for survival in a place it was never meant to be. And these are the astronauts we send for 6 months, a year at most. What will the scans look like after 3 years, after 5, after a lifetime? The dream of becoming a spacefaring species depends on solving this problem, not just mitigating it, not just managing it, but solving it. Because a civilization cannot be built on bodies that break. Children cannot grow strong in an environment that hollows their bones. Families cannot thrive if every generation is weaker than the last. A future among the stars requires that the human body can endure, not just for months, but for lifetimes. And right now, we do not know if that is possible. The quiet erosion continues in every astronaut currently in orbit, in every mission being planned, in every calculation of how long humans can survive beyond Earth. The skeleton is dissolving, month by month, cell by cell, and no one has yet found a way to make it stop. But the most dangerous threats in space are not the slow ones. Some arrive in minutes. The sun does not hate us. It does not even know we exist. For billions of years, it has burned at the center of our solar system, a vast nuclear furnace converting hydrogen into helium, mass into energy, oblivious to the fragile life clinging to a small world in its orbit. Most of the time, we are safe. Earth's magnetic field deflects the solar wind. The atmosphere absorbs what gets through. Life beneath this double shield has flourished, never knowing how close it lives to annihilation. But in space, there is no shield, and sometimes, without warning, the sun erupts. Solar particle events. The name sounds technical, sterile. It does not convey the violence of what it describes. A sudden explosion on the sun's surface, a solar flare, a coronal mass ejection, releases energy equivalent to billions of nuclear weapons. Plasma and radiation surge outward in all directions, and embedded in that surge are protons, billions upon billions of them, accelerated to nearly the speed of light. They race across the void, and if a spacecraft happens to be in their path, there is almost no warning, minutes at best. Satellites near Earth might detect the event and send an alert, but the particles are already traveling at 40% the speed of light or faster. By the time the warning arrives, the storm may already be upon you. On Earth, we would barely notice. The atmosphere would absorb the protons. We might see auroras, brilliant and strange, dancing across skies where they do not usually appear. Power grids might flicker, satellites might glitch. But we would be safe. In space, there is nowhere to hide. The spacecraft walls offer some protection. Aluminum, composite materials, layers of insulation. But they are thin. They have to be. Every gram of mass requires fuel to lift into orbit, fuel to accelerate, fuel to slow down again. Engineers balance protection against practicality, knowing they can never make the walls thick enough to stop everything. And a solar particle event does not need to penetrate completely to kill. Even partial shielding still allows a lethal dose through. The protons pass through the hull as if it were paper. They pass through spacesuits, through equipment, through the bodies of the crew. As they travel, they ionize atoms, ripping electrons away, leaving trails of chemical chaos in their wake. In living tissue, this chaos is devastating. DNA strands snap, cell, and membranes rupture. The delicate machinery of life, proteins, enzymes, the molecular systems that keep cells alive, begins to fail. The damage is invisible at first. There is no pain, no immediate sign that anything is wrong. But the body knows. Acute radiation syndrome. It arrives in stages, each one worse than the last. Within hours, the prodromal phase begins. Nausea, vomiting, dizziness. The crew members feel sick, profoundly sick, but they do not yet understand why. They might think it is motion sickness, stress, contaminated food. Then it passes. For a few days, they feel better. This is the latent phase, a cruel reprieve. The body is mobilizing its defenses, trying to repair the damage. But the damage is too extensive, too deep. And the cells that divide most rapidly, the lining of the gut, the bone marrow, the immune system, are already dying. A week later, the manifest phase arrives. The intestinal lining sloughs away, causing severe diarrhea and internal bleeding. The immune system collapses, leaving the body defenseless against infection. The bone marrow stops producing blood cells. Anemia sets in, platelets vanish, and bleeding becomes uncontrollable. Without aggressive medical intervention, transfusions, antibiotics, sterile environments, intensive care, the crew will die within weeks. And there is no intensive care unit on a spacecraft. This is not theoretical. Solar particle events happen, not frequently but regularly, several times per solar cycle, which lasts about 11 years. Most are mild, some are moderate, but every few cycles there is one that would be catastrophic for anyone caught in open space. In 1972, between the Apollo 16 and Apollo 17 missions, a massive solar particle event erupted. If astronauts had been on the moon at that moment, outside the minimal protection of the lunar module, they would have received a lethal dose. They were lucky. The timing was wrong for them, but right for survival. But luck is not a strategy. Engineers know this. They have designed contingencies. On long-duration missions, spacecraft carry what are called storm shelters, small, heavily shielded compartments where the crew can retreat if a solar particle event is detected. These shelters are not comfortable. They are cramped, just large enough for the crew to squeeze inside and wait. The walls are lined with water tanks, storage containers, anything with mass that can absorb protons. The idea is to create a makeshift barrier, a temporary refuge until the storm passes. It might take hours, it might take days, and the crew sits in the dark, surrounded by their own supplies, knowing that just beyond those thin walls, invisible particles are streaming past, carrying enough energy to destroy them. On Mars, the solution would be different. Martian habitats would likely be buried under regolith, the loose, rocky soil that covers the surface. Meters of it, piled on top of inflatable domes or prefabricated structures. The regolith absorbs radiation far better than any metal or composite material, but this means living underground, or at least under a thick blanket of dirt and rock. Sunlight would be filtered, indirect. The habitats would feel less like homes and more like bunkers. And during a solar particle event, the crew would retreat even deeper into storm shelters dug into the Martian soil itself, waiting, hoping the event ends before their supplies run out, before claustrophobia and fear take their toll. Some researchers have proposed more ambitious solutions. Magnetic shields that mimic Earth's magnetosphere, deflecting charged particles away from the spacecraft. These are not fantasies. The physics is sound, but the engineering is staggering. The amount of energy required to generate a magnetic field strong enough to protect the spacecraft is immense. No current power system could sustain it. Perhaps fusion reactors, still decades away from practical use, could provide the necessary power. Perhaps superconducting magnets, cooled to near absolute zero, could generate the field with less energy. But these are maybes, hypotheticals, dreams of a future technology that does not yet exist. And in the meantime, astronauts remain vulnerable. There is another approach, a biological one. What if the body itself could be made more resistant to radiation? This is not as far-fetched as it sounds. Some organisms on Earth are astonishingly radiation resistant. Deinococcus radiodurans, a bacterium, can survive doses of radiation thousands of times higher than what would kill a human. It does this through redundant DNA repair mechanisms, multiple copies of its genome, and enzymes that scavenge free radicals before they cause damage. Could those mechanisms be transferred to human cells? The research is ongoing. Scientists have identified genes responsible for radiation resistance and are exploring ways to introduce them into human genomes, not just for astronauts, for cancer patients undergoing radiation therapy, for survivors of nuclear accidents. For anyone exposed to levels of radiation the body cannot naturally withstand. But the ethical questions are profound. To genetically engineer humans for space travel is to cross a line we have never crossed before. It means altering the human genome not to cure disease, but to enhance capability, to create people who are, in a fundamental sense, different. Is that acceptable? Is it necessary? Or is it the beginning of a future where humans are divided into those who can survive space and those who cannot? There are also drugs, radioprotective compounds that can reduce the damage caused by radiation exposure. Some work by scavenging free radicals, the reactive molecules that radiation creates as it passes through tissue. Others stimulate DNA repair pathways, helping cells recover from damage more quickly. These drugs exist. Some are approved for use in radiation therapy. Others are experimental, tested only in animals or in vitro. but none of them can fully protect against a severe solar particle event. They can reduce the damage, they can improve survival odds, but they cannot make a human immune to the storm. So, the gamble remains. Every mission beyond Earth's protective bubble is a roll of the dice. Will the sun remain quiet? Will the crew make it to their destination and back before the next major solar particle event? The odds are calculable. Scientists can estimate the probability based on historical data, solar cycle predictions, current activity. For a 6-month mission, the risk is low but not negligible. For a 3-year mission to Mars, the risk becomes significant. And for a permanent presence in space, for colonies and settlements and generations living beyond Earth, the risk becomes a certainty. Eventually, inevitably, there will be a solar particle event that catches people unprepared, away from their shelters, on the surface during an EVA, in transit between habitats, and they will die. This is the bargain we make with space. It offers infinity, the cosmos in all its vastness spread before us, the promise of new worlds, new knowledge, new futures. But it demands payment, not just in money or resources or time, in lives, in the certainty that some who venture beyond Earth will not return, that some will be killed by forces so immense, so indifferent, that our best technology can only barely blunt their edge. The sun will erupt again. It always does. And when it does, the particles will stream outward, crossing millions of kilometers in minutes, blind and unstoppable. Somewhere, someone will be in their path. There is a strange intimacy to this danger. Cosmic radiation, the background exposure that slowly accumulates over months and years, feels abstract, distant. A risk assessed through statistics and probabilities. But a solar particle event is immediate, personal. It is the universe reaching out and touching you, directly and violently, in a way that leaves no ambiguity. You were in the wrong place at the wrong moment, and the consequences are absolute. Astronauts train for this. They run simulations. They practice retreating to storm shelters, timing how quickly they can move from one module to another, calculating how long their supplies will last, if they have to stay sealed inside for days. They know the risks, they accept them, but acceptance does not erase fear. When the alert comes, when sensors detect the first arrival of high-energy protons, there is a moment of pure primal terror, the instinct to run, even though there is nowhere to run. The knowledge that an invisible wave of destruction is washing over the spacecraft, passing through walls and bodies alike. And the waiting, the helpless waiting, sealed inside a metal box surrounded by water tanks, hoping the shielding is enough. Hoping you chose the right shelter, hoping the event is not as strong as it could be, hoping the sun, in its vast indifference, shows mercy. But the sun does not know what mercy is. It is a star, a ball of fusing hydrogen, governed entirely by physics. It erupts because magnetic field lines tangle and snap, because pressure builds and must be released, because this is what stars do. And we, fragile and brief, exist at the edge of its fury, trying to carve out a future in a realm that was never meant for us. Some say this makes space exploration noble, that to face such danger and continue anyway is the highest expression of human courage. Others say it is hubris, that we are risking lives for dreams, pushing into environments we cannot safely inhabit, building futures on foundations that may collapse at any moment. Both are true. The nobility and the hubris are inseparable. And so, the missions continue. Plans for Mars grow more detailed. Designs for lunar bases become more refined. The technology improves, slowly, incrementally, edging closer to something that might actually keep people alive in the long term. But the sun remains what it has always been, a source of light and life for the world that orbits it, and a source of sudden, invisible death for anyone who ventures too far from that world's protection. The killer in the light does not announce itself. It does not give fair warning. It simply is. a fact of existence as fundamental as gravity, as inescapable as vacuum. And anyone who travels through space must live with the knowledge that at any moment, without warning, the light itself could turn lethal. Survival is not only physical, space also reshapes the unseen world inside us, the world ruled by microbes, fear, and isolation. We think of ourselves as singular beings, one body, one mind, one consciousness navigating the void. But that's never been true. You are not alone in your own skin. Right now, trillions of microorganisms live inside you, on you, around you. Bacteria, fungi, viruses, archaea. They outnumber your human cells. They produce chemicals that regulate your mood, train your immune system, digest your food, even influence which thoughts rise to the surface of your awareness. You are not an individual, you are an ecosystem. And when that ecosystem leaves Earth, something changes, something quiet, something we didn't expect. The microbiome begins to drift. In the controlled sterility of a spacecraft or space station, the diversity of your microbial passengers starts to collapse. Back on Earth, you encounter thousands of species every day. You brush against soil, breathe forest air, touch doorknobs, shake hands, eat fresh vegetables pulled from the ground. Each contact renews your inner garden. But in space, there is no garden. There is only the ship. It's the same recycled air, the same crew, the same surfaces, wiped down with antiseptics again and again. The same freeze-dried meals, irradiated to kill contamination. At first, nothing seems wrong. Astronauts feel fine. They perform their duties. They smile for the cameras. But beneath the surface, their microbiomes are quietly shrinking. Species that once thrived in their guts begin to fade. Beneficial bacteria that produce vitamins, regulate inflammation, defend against infection. They need variety to survive. They need the chaos of Earth's microbial abundance. In the sterile quiet of space, they starve. And as they disappear, the immune system begins to falter. Not all at once, not dramatically, just a slow, creeping vulnerability. Wounds take longer to heal. Infections become more likely. Inflammation rises without clear cause. The body, sensing the loss, starts to panic in ways it cannot articulate. But the microbiome doesn't just vanish, it transforms. Because nature abhors a vacuum, and when beneficial species fade, something else moves in to fill the empty niches. Often, it's the opportunists. The bacteria that were always there, kept in check by competition, suddenly find themselves without rivals. They multiply. They change. Some species that were harmless in small numbers become dangerous in large ones. Others, responding to the stress of the environment, activate genetic programs that make them more aggressive, more resistant to antibiotics, more capable of breaching the barriers that normally keep them contained. The microbiome, once a peaceful coalition, becomes unstable. And then there's the stress. Space is not gentle on the human psyche. The isolation, the confinement, the knowledge that you are suspended in a metal shell in a place that wants you dead, the sleep deprivation from shifted circadian rhythms, the constant low-level anxiety that something, somewhere, might go wrong. Your body responds to this stress the way it always has. Cortisol floods your bloodstream. Adrenaline spikes. Your immune system, already compromised, is pushed even further off balance. And in that chaos, old enemies wake up. Viruses you forgot you had. Herpes simplex, Epstein-Barr, varicella zoster. The virus that gave you chickenpox as a child and then went dormant in your nerve cells, waiting. On Earth, your immune system keeps them asleep. But in space, with your defenses weakened and your body under siege, they sense an opportunity. They reactivate. Astronauts on long missions have reported strange symptoms, cold sores that appear without warning, shingles flaring up, mysterious rashes. viral shedding detected in saliva and urine, sometimes for weeks, sometimes for the entire duration of the flight. The viruses aren't new. They were always there, passengers carried from Earth, dormant and patient. Space just gave them permission to move. And it's not only viruses, bacteria too begin to shift. Studies of microbial samples collected aboard the International Space Station reveal something unsettling. Strains of common bacteria, harmless on Earth, develop mutations in space. They grow thicker cell walls. They produce more biofilm, making them harder to kill. They become more virulent. Some develop resistance to antibiotics faster than they would on the ground. It's as if space accelerates their evolution, pushes them towards survival strategies that make them more dangerous, more difficult to control. The very microbes you brought with you, the ones you depend on, are being reshaped by the same hostile environment that reshapes your bones and blood and brain. And then there is the deeper question, the one we're only beginning to ask. What happens when the microbiome changes the mind? Because it does. We know this now. The gut-brain axis, they call it. A communication network linking the trillions of bacteria in your intestines to the neurons in your brain. These microbes produce neurotransmitters, serotonin, dopamine, GABA. They send chemical signals up the vagus nerve, influencing mood, memory, decision-making, even personality. When your microbiome is healthy, you feel balanced. When it's disrupted, you don't. Depression, anxiety, cognitive fog, all have been linked to microbial imbalance. So, what happens on a long mission when your microbiome has been shrinking, shifting, destabilizing for months or years? When the beneficial species that once kept you steady are gone, replaced by opportunists and stress-adapted survivors? Do you still think clearly? Do you still feel like yourself? Or does something subtle change? A creeping irritability you can't explain, a sense of disconnection, thoughts that don't quite feel like your own. Astronauts on the ISS have reported mood swings, periods of intense frustration or sadness that seem to come from nowhere. Some describe it as a kind of emotional fragility, a feeling that their usual coping mechanisms no longer work. Is it just the isolation, the confinement, the separation from loved ones? Or is it something deeper, something microbial? If the bacteria in your gut are producing different chemicals than they did on Earth, then the brain receiving those signals is no longer the same brain. It's been subtly altered, retuned to a different frequency. And if that's true, then the person who returns from a long mission to Mars or beyond might not be quite the same person who left. Not in some dramatic science fiction sense. No alien possession. No violent transformation, just a quiet drift, a shift in the inner landscape, small changes in temperament, in perception, in the way emotions rise and fall, enough that they notice, enough that others notice, but not enough to name it, or fix it, or understand what was lost. This is the haunting question at the center of long-duration spaceflight. We can track bone density. We can measure radiation exposure. We can monitor heart function and muscle mass. But how do you measure the self? How do you quantify the slow erosion of the microbial community that helps make you who you are? And if that community cannot be preserved, cannot be restored, then who exactly comes home? There are proposals, of course, ideas to protect the microbiome, probiotic supplements, freeze-dried fecal transplants to restore lost diversity, bioreactors aboard spacecraft, cultivating beneficial bacteria in controlled environments. Some researchers suggest bringing pieces of Earth along, soil samples, plants, creating small living ecosystems inside the ship, reintroducing the microbial chaos that humans evolve with. Others argue for something more radical, designing synthetic microbial communities, optimized for space, bacteria engineered to thrive in low gravity, high radiation, sterile habitats, a new microbiome for a new environment. But that raises its own questions. If we replace Earth's bacteria with something else, something designed for space, do we stop being human in some fundamental way? And if we don't, if we insist on carrying Earth's microbes with us, can they survive where we're going? Or will they die, species by species, leaving us alone in our own skin for the first time in evolutionary history? There's a strange poetry to it, if you think about it. Humanity reaching for the stars, only to discover that we cannot go alone, that the invisible passengers we've carried for millions of years are fragile in ways we never imagined. That exile from Earth means exile from the microbial world that made us. And without them, without that ancient partnership, we are something less than we were. Not broken, perhaps, not destroyed, just diminished, simplified, alone. The implications stretch far beyond biology. They touch on identity, on continuity, on what it means to remain yourself when every system that sustains you is being quietly rewritten. With every system stretched, strained, or rewritten, we confront the central question: should humans adapt space to the body or the body to space? Because the choice is no longer abstract. It's written in the genes of bacteria mutating aboard the ISS. It's felt in the mood swings of astronauts on long missions. It's waiting in the sterile habitats we plan to build on the moon, on Mars, in the long dark between stars. And whatever we decide, we'll carry it with us. Or we won't carry it at all. We've spent 6 chapters cataloging the damage, the bones that crumble, the eyes that warp, the hearts that forget how to pump, the microbiomes that fade into sterile silence. Space, we've learned, is not kind to the human form. But here's the thing about humanity. We don't accept limits easily. When nature presents an obstacle, we build a bridge. When the environment becomes hostile, we change it. When our bodies fail us, we engineer solutions. So, the question now is not whether space will harm us. We know it will. The question is what we're willing to do about it. Because the answers we're considering, the technologies we're developing, the interventions we're debating, they don't just solve problems. They force us to confront something deeper. They force us to ask who we are and who we're willing to become. Let's start with the simplest solution, the one that seems obvious: artificial gravity. If the problem is weightlessness, then create weight, spin the habitat, use centrifugal force to push bodies against floors, simulating the pull of Earth. Give bones a reason to stay strong. Give hearts a load to work against. Give the inner ear a consistent sense of up and down. It's elegant. It's mechanical. It doesn't require changing the human body at all, but it's not simple. Building a rotating space station large enough to generate comfortable artificial gravity without making people nauseous requires engineering on a scale we've never attempted. The structure has to be massive. The rotation has to be slow enough that the difference in centrifugal force between your head and your feet doesn't make you dizzy. That means a radius of hundreds of meters, maybe more. It means launching thousands of tons of material into orbit. It means construction projects that dwarf the International Space Station. It means costs that spiral into the hundreds of billions, maybe trillions. And even then, it only works for people inside the station. The moment you step outside, the moment you need to repair a solar panel or explore a planetary surface, you're back in low gravity. Your body starts the adaptation process all over again. So some researchers ask a different question. Can we skip the spin? Can we replace gravity with something else? Exercise regimens carefully designed, resistance bands and treadmills, pharmaceuticals that trick bones into staying dense, muscles into staying strong, electrical stimulation, vibration platforms, gene therapies that activate the cellular pathways normally triggered by weight-bearing activity. It's an appealing thought. No massive rotating structures, no astronomical budgets, just medicine and discipline. But here's the uncomfortable truth. It doesn't work. Not fully, not yet. Astronauts on the ISS already exercise 2 hours a day, every day, with equipment specifically designed to load their bones and muscles. They take supplements, they follow protocols developed over decades of research, and they still lose bone density. They still lose muscle mass. They still come home weaker, because exercise and weightlessness is not the same as living in gravity. Gravity is constant. It loads your skeleton with every step, every moment you stand, every time you simply exist upright. Exercise is intermittent, focused. It targets specific muscle groups but can't replicate the full body, 24-hour loading that Earth provides. So, maybe the answer is better pharmaceuticals. Drugs that prevent bone resorption, stimulate muscle growth, regulate fluid shifts, compounds that mimic the effects of gravity at the cellular level. But then we're talking about astronauts taking cocktails of medications for months or years, drugs whose long-term effects in space are still unknown. We're talking about altering human physiology with chemistry, not to cure disease, but to compensate for an environment we were never meant to inhabit. And that brings us to the harder question. If we're already altering the body with drugs and exercise regimens that don't quite work, why not go further? Why not change the design itself? Radiation is the clearest example. We know cosmic rays and solar particles will shred DNA over time. We know that, on a mission to Mars, astronauts will absorb doses that significantly increase their cancer risk. We know that beyond Mars, beyond the heliosphere, the radiation environment becomes even more hostile. The conventional solution is shielding. Build thicker walls, line spacecraft with water tanks, surround habitats with regolith, create safe rooms where astronauts can shelter during solar storms. But mass is expensive. Every kilogram of shielding is a kilogram of fuel you need to launch, to accelerate, to decelerate. And even thick walls don't stop everything. High-energy particles punch through meters of material. Perfect shielding would require walls so heavy that the spacecraft becomes impossible to move. So some scientists propose a different approach: make humans radiation resistant. It sounds like science fiction, but the biology already exists. Certain organisms on Earth, extremophiles, survive radiation levels that would kill a human 1,000 times over. Tardigrades, Deinococcus radiodurans. They have mechanisms to rapidly repair DNA damage, to protect cellular machinery, to shrug off exposure that would be lethal to us. We're learning how those mechanisms work. We're learning how to code them into genes. And gene editing technology, CRISPR, and its successors now gives us the ability to rewrite the human genome with precision. So, the question is no longer whether we could create radiation-resistant humans. The question is whether we should. Imagine an astronaut whose cells carry backup copies of critical genes, ready to replace damaged sequences, whose DNA repair systems work 10 times faster than yours or mine, whose body produces compounds that neutralize free radicals before they cause harm. That astronaut could survive a mission to Mars with minimal cancer risk, could explore the outer solar system without hiding behind walls of lead, could spend years in deep space and come home healthy. But they would no longer be quite human, not in the way we understand it now. They would be something we designed, something we built, a person engineered for an environment that natural selection never prepared us for. And once you start down that path, where do you stop? If we can edit genes to resist radiation, why not edit for bone density that doesn't fade in weightlessness? Why not enhance muscle efficiency, reduce oxygen requirements, improve tolerance for carbon dioxide? Why not redesign the cardiovascular system to function optimally in low gravity? Why not alter the microbiome, programming synthetic bacteria that thrive in sterile spacecraft and produce exactly the neurotransmitters we need? Why not build humans for space from the ground up? There are researchers right now who argue this is inevitable, that trying to keep Earth-adapted bodies alive in space is like trying to keep tropical fish alive in the Arctic. Possible, with enough effort and technology, but fundamentally inefficient. They argue that if we're serious about becoming a spacefaring species, we need to accept biological modification as a tool, the same way we accepted vaccines, antibiotics, and corrective surgery. But others push back, hard, because genetic modification is not just a medical intervention, it's a redefinition. Once you start engineering humans for specific environments, you create divergence. People designed for Mars may not thrive on Earth anymore. People adapted for low gravity may find Earth's pull crushing. People with radiation-resistant genes may pass those genes to their children, who never asked to be born different. You create subspecies, branches, variations of humanity adapted to different worlds. And at some point, those branches may drift so far apart that they're no longer the same species at all. This is the identity dilemma. At what point do we stop being human? Is it when we edit our DNA? When we replace biological functions with machines? When we alter our minds with synthetic microbiomes? When we give birth to children who cannot survive on Earth, only on the worlds we've built for them? There's no clear line, no moment where you can point and say, here, this is where humanity ends and something else begins. It's a gradient, a slow transformation. But make no mistake, the transformation is real. Some ethicists argue that we have a moral obligation to preserve the human form as it is, that we evolved on Earth for a reason, and that changing ourselves to fit other environments is a kind of violence, a rejection of our evolutionary heritage. Others argue the opposite, that evolution never stopped, that humanity has always modified itself through culture and technology, and that genetic engineering is just the next step. That clinging to our current form is arbitrary, even cowardly, when the tools to improve it are within reach. Both perspectives have weight, both carry consequences. If we refuse to modify ourselves, then space exploration remains limited, dangerous, expensive. We'll need massive infrastructure to keep fragile Earth bodies alive in places that want them dead. We'll lose astronauts to radiation, to bone fractures, to immune collapse. We'll pour resources into life support systems that will never be perfect. But if we embrace modification, we open doors we may not be able to close. We create ethical questions that have no precedent. Who decides which modifications are acceptable? Who gets access to them? What happens to people who choose not to be modified or can't afford it? What happens when enhanced humans and unmodified humans no longer see each other as kin? And perhaps most troubling of all, what happens if we're wrong? What if we engineer radiation resistance, but it comes with unforeseen costs? What if modified immune systems fail in unexpected ways? What if children born with space-adapted genes suffer in ways we didn't predict? Evolution is slow for a reason. It tests changes over thousands of generations, ruthlessly discarding failures. We're talking about making changes in a single generation, with no long-term data, no way to know what we're unleashing. We're playing with code we didn't write and don't fully understand. But here's the thing, we may not have a choice. If we want to reach other stars, journeys that will take decades or centuries, we can't bring Earth with us. We can't build gravity wells large enough. We can't shield against every particle. We can't maintain Earth-like conditions for that long. The people who make those journeys will have to be different. We'll have to be adapted. We'll have to be something more than what we are now, or perhaps something else entirely. And if we don't do it deliberately, through careful engineering, then space will do it for us, through mutation, through selection, through the slow grind of people living and dying in environments that reshape them generation by generation. Either way, change is coming. The only question is whether we guide it or let it happen blindly. There's a weight to that realization, a vertigo that has nothing to do with the inner ear. Because this isn't abstract anymore. We have the technology, we're running the experiments, we're debating the ethics in real time. The future human is not a distant concept. It's a decision we're making now, in labs and conference rooms and policy discussions, often without fully grasping what we're deciding. And once the door opens, once the first genetically modified astronaut steps aboard a spacecraft, once the first child is born with genes designed for Mars, there's no going back. We will have crossed a threshold, become architects of our own evolution, taken responsibility for what we are and what we will become. In the end, the story of space is not about planets or rockets, it's about us and what we are willing to become.